Go.
Hi, my name is Claire Yeager. My group is doing the well optimization project for Biocalc. This is the main equation. N sub t plus 1 is equal to 0.94 n sub t plus n sub t minus 8 brackets of 0.06 plus 0.0567 whatever. I don't know what that is, but it's okay. 1 to the 1 minus the n sub t minus 8 over n sub star to the power of 2.39 all minus 0.94 ct. So now we will go through and talk about what each one of these variables are. So for all of the n subs except n star, that's going to represent the adult female whale population subject to harvesting at that time, t time in years. So t plus 1 will be next year, t minus 8 will be 8 years ago, and then n sub t is right now. So that's t. N sub star is the max number of whale population the environment will support if no harvesting occurs, which is 250,000. Our last variable is c sub t, which is the number of whales harvested that year. It's important to note that n t minus 8 or n sub t minus 8 is referring to when the whales are capable of being harvested, because the whale age for harvesting is greater than or equal to 8 years. So this variable is when the whales can be harvested. Okay. So for problem number 1, we're pretty much proving that if nt and nt minus 8 are equal to n star, then nt plus 1 has to also equal n star. So we took our main equation, and instead of nt and nt minus 8, we plugged in n star, which once you come over here, you get n star over n star. That equals 1. And then we are also looking at when harvesting is 0 for problem number 1. So we pretty much plug in 0 here, and this goes away. And then you get left with this equation of n sub t plus 1 is equal to 0.94 n star plus 0.06 n star, and that adds up. If you add them together, you do the math. You get n sub t plus 1 is equal to 1 n star. So pretty much we proved this correct.
Okay, so my name is Luke Wardekemper, and I'm doing question number 2. This is our equation with 500 whales harvested and 250,000 in the population. We basically just plugged both these numbers in here, and we're assuming that this is a 0.94 constant times our 500 harvested, and we end up we distribute this in and end up getting 470 whales harvested, accounting, and I'll explain what the 0.94 is a little bit later, but it ends up being 470 harvested with a population of 250,000. And then it asks us to, again, reevaluate this equation, this time, once again, with a population of 250,000, but we're supposed to use a 2% of that population. So just a simple multiplication here. We multiply through, we find out that 0.2% of 250,000 is 5,000 whales harvested. We once again just plug that into the same equation that we got from part 1, and we plug it in here next to the 0.94 as CT. We end up getting 4,700. Pretty much the same thing, just a larger number of whales harvested. Part C, it asks us to explain what the 0.94 value is accounting for, and we determined that it accounts for a 6% natural death loss of the whale population. So basically, when you have such a large population like this, there's going to be some whales that are dying naturally and aren't being harvested, so obviously if they're dead, they can't be harvested. So that's what the 0.94 is accounting for. So if there's 5,000 that could be harvested, we actually end up only getting around 94% of them because 6% of them are dying naturally.
Hi, my name is Hootie Lawrence, and I will be working on problem number 3, specifically A, B, and C. So for number 3, what we're ultimately trying to do is find the derivative of the fecundity equation that we were given above. And that equation is the n sub t minus 8 times the 0.06 plus 0.0567 times 1 minus n sub t minus 8 over n sub star to the 2.39 power. For the first part, A, we are going to use the rescaled equation to take the derivative of, at least for me to simplify, substituted x for every ne. So we get x times this big long thing and then x to the 2.39. Distributed this x out in front to each term, and then once again I distributed this x into each of these terms. Ultimately, I took the derivative of each part. So say for the product rule, this is x to the first. We bring down the 1, multiply it by the 0.06, stays at 0.06. And then I'm left with x to the 2.13. So to take like the square root of it, we set that to a power of 1 over 2.39. And so then we're just left with x, what we're trying to find. For part B, if we go over here, we have our beautiful graph, and our graph shows a maximum point, and this is where the derivative is 0 and the horizontal of like the tangent line is horizontal, and that would be 0. And at this point we got what our equation said. We got 0.812 and 0.0668, and we solved that by setting the derivative equals to 0.
Okay, after some modifications of a previous equation, we get that C of n equals 0.06 ne minus 0.06 ne to the 3.39. The max of that graph occurs at 0.6, 0.025507. We're asked what if C equals 0.03. Since 0.03 is greater than the C value at our max, that means that overpopulation, or